So we're going to work through some review when it comes to looking at atomic structures and isotopes. And here's a chart that you will be seeing. And so I just wanted to walk through it together. When we have a notation like this, we can obviously see that it's B boron. And we could look at the periodic table if we wanted to, but we should be able to see everything we want to see just from looking at this notation. If, though, we wanted to double check ourselves, we could look at the periodic table and it would tell me that the atomic number is 5. And we can see that down here, that lower number. So that lower number is the atomic number. That also tells me that it has 5 protons. And because I don't see anything in this top right section as an exponent, that means that there's no charge to it. So it's neutral. And if it's neutral, that means it has 5 positives and 5 negatives. All right, and that also means that my charge is neutral. So you can say 0, or you could say that it is no charge, or you could just say neutral. Okay, now, again, we can tell what the mass number is. That mass number is above the atomic number. So the mass number is 11. And to find the neutrons, that 11 means that that's protons and neutrons. So 11 minus protons, right? Because mass number is protons and neutrons. And this is just protons. So to find neutrons, I take mass number minus protons. So that would tell me that I have 6 neutrons. Okay, now this next guy, I have the atomic number of 17. So for my notation, my 17 is going to be on the bottom. If I have an atomic number of 17, that means I also have 17 protons. Now it tells me that I have 20 neutrons. So if I know how many protons I have and how many neutrons I have, if I add them together, that will give me the mass number. So that would give me 37 as my mass number. So that would be this top number. And number of electrons. So this tells me that I have a charge of -1. That means I have 1 more electron than proton. So if I have 17 protons, I must have 18 electrons. Because 7, I'll do it, let's see, right here in this top right, it's positive. If I have 17 positives and 18 negatives, 17 minus 18 is -1. That would be the charge. So that right here would be a -1. Now I guess I do need to look at the periodic table to see which element has an atomic number of 17 so I can get that symbol. And hopefully you found that that is chlorine, Cl. All right, let's look at this third one. If I have a mass number of 25 and I have 12 protons, if I have 12 protons, that means that my atomic number is 12. And look at the periodic table, Mg is 12, so I'll put that 12 on the bottom. We know the mass number is 25. So to find neutrons, I'm going to do 25 minus 12, so that would give me 13 neutrons. Now if I have 10 electrons, so 12 positives, 10 electrons, so 10 negatives, 12 minus 10 is a charge of +2. All right. Let's look at this next one. It tells me that it's oxygen, and that bottom number 8 is its atomic number, and that's how many protons I have. It tells me right here that my mass number is 18, so 18 minus 8, that means I have 10 neutrons. It also tells me that I have a -2 charge, so that means 2 more electrons than protons. I have 8 protons, so I must have 10 electrons. And if we want to, that tells me that it's a -2 charge, but we could double check this. 8 positives, 10 negatives, 8 minus 10 is -2. Yep. Okay. Who has an atomic number of 29? Looking at the periodic table, it should be copper. And so that'd be 29 down here. It tells me that it has a mass of 66. Now if I were to look at the periodic table and find copper, at the bottom, it says that its mass is 63.546, but here it says 66, so that just means it's an isotope. Not a problem. All right, so to find Let's see, this is 29 because it's protons, so 66 minus 29 should be 37 neutrons. And it tells me here that I have a +2 charge, so I'm going to write +2. So that means it has 2 more protons than electrons. So if I have 29 protons, I must have 27 electrons. And let's just double check the math. 29 positives, 27 negatives, 29 minus 27 is +2. Great. For this next question, I need you to look at your periodic table and find sulfur. Should be atomic number 16, so that tells me that I have 16 protons. If it's neutral, that means if I have 16 positives, how many electrons do I need to be neutral and have a 0 charge? So this 16 minus, it's got to be 16. Right? 16 positives, 16 negatives will give me a neutral charge. Now it tells me that sulfur exists as 4 naturally occurring isotopes. Sulfur 32, 33, 34, and 36. How many neutrons are in each isotope? Well, we're going to take this mass number, 32, and we're going to subtract 16 protons. So we would have 16 neutrons in this guy. For this isotope, 33 minus 16 would give me 17 neutrons. 34 minus 16 would give me 18 electrons, or I'm sorry, 18 neutrons. And this isotope, 36 minus 16, would give me 20 neutrons. 2 of sulfur's isotopes have very low abundance, 0.75% and 0.01%. The other 2 contribute the remaining 99.24%. Which of the isotopes of sulfur is the most abundant? Why? Okay, so let's look at, I'm going to erase these here so we can see this a little bit better. So the low abundance is 33 and 36. So I'm going to cross off 33 and 36 here because they are less than 1%, 0.75 and 0.01%. They have very low abundance. That's not going to affect the average very much. Now it says the other 2 contribute to the remaining 99.244%. That's sulfur 32 and sulfur 34. Now, what is the average atomic mass that's on the periodic table? On the periodic table is 32.06 is its average atomic mass. So, which one of those isotopes is the most abundant? Sulfur 32 or sulfur 34? Well, it's got to be 32 because 32.06 is very close to this guy. This one's probably 93%. This one's maybe 6%, then these guys together are less than 1%. So the biggest abundance is 32 because my average is closest to that one. We then can look at the Lewis dot structure. We're not doing that electron configuration. So if I look at sulfur and think back to looking at how many valence electrons it has, so I'm going to start counting from the third row, the very first. So sodium is 1, magnesium is 2, skip over aluminum 3 electrons, silicon's 4, phosphorus is 5, sulfur is 6. So we would go like this: 1, 2, 3, 4, 5, 6. Sulfur can become a charged ion. What charge does it take? Okay, well, so if I look at sulfur, we know that being full would be like becoming the nearest noble gas. And we can see here that if it has 6 valence electrons and it wants 8, is it easier to lose 6 or to gain 2? Well, it'd be to gain 2. That's definitely the easiest. So if it were to gain an electron here and gain an electron here, so gaining 2 electrons, it would have an electron configuration like argon, right? Argon has 8 valence electrons, and it's only 2 more electrons than what sulfur has. So if it gains 2 electrons, it's going to become a -2 charge. And we're gaining electrons. And if I'm just going to scroll down here, we know that sulfur's common ion is going to mimic argon. Let's sketch this image of an atom of a neutral carbon-14. Okay, so we know it's carbon, so carbon must have 6 protons, which are these positives. If its mass is 14, that means that there's 14 things in the nucleus. That's protons and neutrons. So let's subtract protons. So 14 minus 6 would be 8 neutrons. So in the nucleus, we have 6 protons and 8 neutrons. If it's neutral, that means if I have 6 positives, I have 6 negatives, 6 electrons. Okay, so now let's make this atom. We know that in the nucleus, there are protons and neutrons. So I'm going to draw my nucleus here, and I'm going to do 1, 2, 3, 4, 5, 6. And then I'm going to, for my neutrons, I'm going to draw little circles. 1, 2, 3, 4, 5, 6, 7, 8. And then sulfur is in my 3rd row. Oh, I'm sorry, not sulfur. Carbon. Carbon's in my 2nd row. So carbon is going to have 2 rings of electrons, 2 energy levels of electrons. In the first, there's going to be 2 electrons, because if I look at row 1, there's hydrogen and helium, so that maxes out at 2. And then to get to carbon, in the 2nd energy level, there's 1, 2, 3, 4 electrons. 1, 2, 3, 4. So a total of 6 electrons. Now this is obviously not drawn to scale because we know our nucleus with protons and neutrons is very, very, very small, dense part of the atom, and that looks very large compared to our atom. So that is going to be very small in actuality. Let's move on to this next question. It says, what's wrong with this statement? Neutral sodium becomes the cation Na+ by gaining a proton. Well, while it might seem by going Na to Na plus 1, you might think, oh yeah, let's gain a proton to become +1. But if I gain a proton, I completely change what element we're looking at. So sodium has 11 protons, and this is still Na, so it still has 11 protons. So I can't ever become charged by gaining a proton. I become charged by losing or gaining electrons. So if I look at sodium, sodium's in my 3rd row, my 3rd energy level. Sodium, if it's neutral, has 11 protons and 11 electrons. So we'll say P+ and E-. Well, if I have Na plus 1 and I have 11 protons, how many negatives do I need to be +1? That's how I like to set it up. So it kind of looks like that. 11 positives minus how many to have +1? Well, this must be 10. So I did not become a cation by gaining a proton. I became a cation Na+ by losing 1 electron. For our next question, in a sample of 400 lithium atoms, it's found that 30 atoms are lithium-6 and 370 atoms are lithium-7. Calculate the average atomic mass for lithium. Well, the first thing I did was, we've been finding our percents with looking at percent abundance. So I'm going to take that 30 atoms and divide it by 400, and that gave me 7.5%. And then 370 divided by 400 times it by 100, and it gave me 92.5%. So now I can take these percents and times it by the mass and go back to what we what we were doing before. So I'm going to take that 7.5%, which is 0.075, and times that by 6.015. And then I'm going to take my 0.925, times that by this mass, 7.016. All right, I just plugged those into my calculator. So I got my two answers. I added them together, and that gives me my AMU, my average atomic mass units. Okay, for the next one, we're calculating the atomic mass for iron, given the data for its natural isotopes. And there's 4 different isotopes. We're given the percentages. So first thing I did was made my percentage into a decimal. Be very careful with this part. Remember, we move the decimal back 2 spots to make the decimal. And it's easy to mess up on these little percentages by not having enough zeros. Then we're going to multiply the AMU for the isotope times that percentage as a decimal. Let's get our 4 answers and add them up. Okay, so check my math, check your math, and let's look to see if it makes sense. I got an average of 55.847, and I just want to double check. If I look at my biggest percentage of my iron isotope, it had a mass of 55.935, so really close to 56, and that was over 90%. So am I close to 56? Yes. And my second greatest percentage was a mass of 54. So somewhere between 54 and 56, yes, that definitely makes sense.